Okay, so today we will discuss the concept of complex numbers. It usually appears at the beginning of a linear algebra course or at the end of a proofs course in algebra. We will explore their properties, what is a complex number, and we'll do some practice problems at the end. So we call a complex number, again, it's just an abstract object. We call this complex number, we call it I, it's a complex number, to be the square root of -1. We call I is a complex number, and it is equal to the square root of -1. So we defined I to be this object that's equal to the square root of -1. And we say that I squared is -1. Its purpose, why we care about it, is because when we want to know the solutions to this equation here, and we try to analyze solutions from any of these sets, we have no solutions. We can't find any options. In other words, what number can you square here to get 0? I mean, whatever number you put here, remember x squared is positive for all sets n, r, q, and z. All those sets, x squared is positive. So how do you get 0? You have to introduce this idea of the complex number and the complex number I. Because now if we define I squared to be -1, if we let x equal I, then x squared is -1. So then x squared plus 1 is indeed -1 plus 1, which is 0. So we solved the problem. So this is why we like to introduce the idea of complex numbers. And they also, if you want applications, they also arise in electrical engineering, mechanical engineering, computer science, physics, etc. So, definition. We say that z equals a plus bi is a complex number in standard form, where a and b are real numbers. So a and b are real numbers, and we know I is, of course, -1. I is the square root of -1. So I here, I is square root -1. Okay? So now we call the real part of z, to, as we denoted, this is our denotion for the real part of z, we call that to be a. That's just this part here. And we call the imaginary part to be b. That's just this part here. So we call the real part and the imaginary part of the complex number. Okay? So, for example, if z equals 2 minus 3i, then the real part of z equals 2, and the imaginary part of z, well, this may be a little confusing, but remember, we can always rewrite this as 2 plus -3i. So therefore, the imaginary part of z must be -3. Okay, remember, this is the real part, this is the imaginary part. And this is just how it's defined. Now we move on to some properties of complex numbers. If we have two complex numbers, z, x plus yi, and w, u plus vi, then they're equal if and only if the real parts are equal and the imaginary parts are equal. This makes sense. This is logical. If we want to add them, then we just add the real parts and we add the imaginary parts. Now the multiplication may be a little tricky. The multiplication, you first take the product of the, oh, I'm sorry, this should be an x here. You first take the product of the real parts, then you take the difference from that, the imaginary parts, then you take the product of the real part and the imaginary part, add that to the imaginary part and the real part of the second complex number. So that's the rule for this one. It's just a rule to memorize. Now, if the real part of z is 0 and the imaginary part is non-zero, then we say that z is purely imaginary. It has no real associated part. And if the imaginary part of z is 0 and the real part is non-zero, then we say it's purely real, it has no imaginary part. If they're both 0, then we say they're both purely real and purely imaginary. If it doesn't make sense, again, these are just definitions. They're just how we define complex numbers. It's just how we define the complex numbers. If it doesn't make sense, again, it's just how we define this object. Now we move on to another definition. The complex conjugate. It's quite an important operation. The complex conjugate of a complex number z, a plus bi, we denote it as, you can say z, there's a bar on top of it, so it's a z with a bar on top, as a minus bi. So all that changes here is that the sign of the imaginary part of z flips. That's the conjugate. The sign of the imaginary part flips. And the complex conjugate, again, is a useful tool when we further analyze linear algebra or advanced operations in complex numbers. So let's apply this with some practice problems. Let's apply the theory. Question number 1. State the real and imaginary parts of each complex number. So z, it's a complex number that's actually a product of two complex numbers. And if we want, right now, we can't read off what the real and imaginary parts are. We have to actually perform the operation. So how do we take the product of two complex numbers? We go back to rule number 3, and that is we take the product of the real parts, so that's 2 times 3, minus the imaginary parts, so that's root 3 times root 3, and then we do this here, it's the xu, so it's the 2 times the root 3 plus the y, sorry, it was the xv plus the yu. So it's plus the yu. And you can simplify this if you want. That's not, I'm not too concerned with that. 6 minus 3 plus 2 root 3 plus 3 root 3i. And so that's 3 plus 2 root 3 plus 3 root 3i. And of course, we can combine this, make this 5 root 3i. So now we can just read out the imaginary part here of z is 5 root 3, and the real part of z is 3. Now, if we have a complex number equal to 3, recall this has no imaginary part. Recall from rule number 4, the imaginary part, rule number 5, if the imaginary part is 0 and the real part is non-zero, then it's just purely real. So then it's just the imaginary part here is 0 and the real part is just 3. I know it seems easy, but you have to get comfortable with the idea of imaginary parts, real parts of complex numbers. Okay, number 3, z is the product of 2 plus 12i, the conjugate of 2 plus 12i times 12 plus I. So first, let's simplify the conjugate. How do we take the conjugate of this number? Again, the sign of the imaginary part just flips. So it's 2 minus 12i. It's 12 plus I. And again, using our rule from before, this is just 2 times 12 minus 12 times 1 plus 2 times 1 plus negative 12 times 12i. And to simplify this quickly, it's just 36 minus, here we get 142i. Okay, now, if you're wondering, does complex number multiplication work like foiling? And the answer is yes. So if we have here a plus bi times c plus di, it works like FOIL. So it is really just AC plus ADI plus BCI and then plus BDI squared. But remember, I squared is negative 1, so that's why we get AC minus BD plus AD plus BCI. Okay, so it works like FOIL, just a fun fact. Number 4, Q is equal to 16I squared. Oh, so what's the real part here? Real part of z, of course, 36, and the imaginary part of z is, remember, it's negative 142. Okay, this reasoning is similar to what we described here. So 16I squared, let's simplify that. That's 16 times negative 1, so the negative 16. So again, it's just the real part of q. Negative 16, and the imaginary part is 0. Now let's move on to proofs. Again, proofs are really the heart of math. This is how you really test if you understood a concept well. So let z be a plus bi and prove that z times z bar is purely real. So z bar is equal to a plus bi times a minus bi. And using our multiplication formula, this is a squared minus b squared plus minus ab plus ab I. This ends up being a squared plus b squared plus 0i. And 0 times I is a nice unique property. 0 times I is 0. I know it may seem obvious, but because we're dealing with a new object, we have to make sure that we're clear what is allowed and what is not allowed. And this is allowed. 0 times I is 0. So it is just a squared b squared. And since a squared, b squared is real. Or since the imaginary part is 0, so since imaginary part of ZZ bar is 0, ZZ bar is pure real.